Okay, we're going to talk about infrared spectroscopy in this video, and I'm going to show you some infrared spectra. There's one in front of you there, but just so you know, these are all available from this website here, and so you've got to give them an acknowledgement. That's where I got them from. Okay, so right, what does infrared spectroscopy tell us then? It will tell you, it won't let you identify a molecule unambiguously, but it will tell you what functional groups are in it. So if it's got an alcohol in it, you can tell the molecule very easily it's got an alcohol. You can spot if it's carboxylic acid, but what you can't tell the difference if it's ethanoic acid or propanoic acid or butanoic acid. It won't give you that sort of level of information, but it will tell you which functional groups are in the molecule. So how does it work? Right, so you get, there's a sample, so it's not in a test tube, I'll just draw a test tube, and infrared light is shone through it, and you have a detector there, what it detects. Okay, right, and the frequency of this is changed. Okay, so it starts off at low frequency, and it moves, the light moves, the infrared moves through different spectrums to a higher frequency, and so you end up with a graph where you have, if I just draw a little sketch, you have frequency along the bottom, and this is the amount of light, not absorbed, but the amount of light let through, so the amount of infrared that gets through. So here, 100% of the infrared is getting through. So when I'm drawing there's no absorption, and then this frequency gets absorbed. So you get that like that, and then none is absorbed, and then you might get another one where it's absorbed. Okay, so different functional groups absorb infrared at different frequencies. So by where these troughs are, you can tell which functional groups in the molecule. There's a few little oddities about infrared. Right, first of all, they call them peaks, but you can see they're not peaks at all. They're actually troughs, aren't they? Yeah, and they say certain peaks correspond to certain functional groups. So let's have a look at a real spectrum instead of my little picture of it. Okay, so you can see on this axis here, you might be able to see it actually says transmittance. So, and that's 100% there, that's 100. So that means all the light is going through, all of the infrared is going through. Now along this bottom here, now I said that you had frequency, but if you look there, it actually says it's got this rather strange thing called a wave number, and the units of that are per centimeter. So here, this has got 500 per centimeter. That means you can fit 500 of your wavelengths into 1 centimeter. So the bigger the wave number, the the higher the frequency. So wave number is just rather, instead of measuring it in hertz, it's measured in wave number per centimeter. Right. Another bit of a funny thing is you'll see that this scale goes backwards. Okay, so it starts off here at that's at 4,000, and it ends up here at 500. Another funny thing about it is it's not linear. If you look, there's 3,000 there, there's 2,000 there, but there's 1,500. That's 1.5. Yeah, and there's, so they kind of change the scale as they go along the bottom, and that's always the way it's been done, and we're stuck with that. Okay, now this is the spectrum for methyl propan 2-ol, and you can see, well, which bonds do we have in here? We have carbon, we have carbon-carbon bonds, we have carbon-hydrogen bonds, but there, if you think about it, that's not going to be very useful, is it? To know a molecule's got carbon-carbon bonds in it, well, practically every organic compound has them in it, so that's not much use at all. To know it's got carbon-hydrogen bonds in, that's not very useful either, because they've all got them. So let's just have about what things are useful. Now here, you are given this on the back of your periodic table in the exam, so you don't have to remember any of this. And it tells you which bond corresponds to which wave number. So NH and amines is quite far to the left, 3,000, yeah, 300 there. Alcohols, which is what we've got here. Now you can see it says between 3,200 and 3,550. Well, this, if you look at the scale, is the peak for the OH. It's the OH in the molecule which is causing that. And this peak next to it, well, if you look there, look at the value for CH, that's what this is. This is CH. And as I say, that CH peak is not very useful because everything has got that. But what it is useful to know that this is an alcohol. Now, when you get used to looking at these spectra, it won't take very long. Probably what you look at more, rather than looking at the actual wave number and looking at the scale down here, you know, it's the shape of these peaks. This sort of double peak thing is extremely characteristic of an alcohol. So, whenever you look at spectrum, your eyes go to the left. If you see that double peak there, you know you've got an alcohol. You can check the wave number afterwards, but that is that due to the OH and the CH next to each other, you know, this sort of shape, that is always characteristic of an alcohol. Right, now you probably noticed that after about here, so from 1500 onwards, down to about 500, it looks like there's lots and lots of peaks, isn't there? And that bit, you can't say that one peak is due to a certain bond. It's not possible to do that. It looks very random. And this is called the fingerprint region. So you may think you can't say which peak is corresponding to which particular bond, so you may think it's not that useful. But it is useful in a way because it's unique to each molecule. So that means if you have a library of these fingerprint regions, they used to be done by eye, now it's done by computer. You've got a library of thousands and thousands of different compounds. So if you make a new compound, then you can match this fingerprint region to the database and say, oh, that must be methylpropan-2-ol. So the fingerprint region, yeah, does give you information, but it doesn't tell you which bonds. Whereas all of this bit of the spectrum, this is, you can say, yeah, you get a peak in a certain place there, is due to the presence of a certain kind of bond. Just to show you, so that's methylpropan-2-ol. And before we finish this video, right, here is, this is butan-1-ol. And you can see how similar those two things are. I'll try and squeeze it down to get it to so you can see them together. Try and shrink it a bit, yeah, that's it. Okay, look how similar those two spectra are. You've got this very characteristic double peak, haven't you, for very characteristic of an alcohol. You've got the OH and the CH next to each other. Here, you've got the same thing again. But you can't tell which alcohol it is. You can just know it is an alcohol. But then you could have a look at the fingerprint region, and if you could try and match it up that way. Right, let's have a look at some of these values which AQA have given you. And it is, to be perfectly honest, a little bit more trouble than it's worth, this thing here, because you tend to spot these functional groups not really by looking at the wave numbers, but by the shape of them. There's not many to learn, and very quickly you'll learn to recognize which are which. So I just tell you, for example, all of this lot down here, well, these two here, carbon oxygen bond and carbon carbon bond, well, first of all, everything's got a carbon-carbon bond. It's not very useful, but they're not useful because they're in the fingerprint region. So that means it's difficult to interpret because you've got lots and lots of sort of random peaks there, and you can't really tell what's going on. So you can forget about them. I tell you the ones that are really important, and they always ask because they're easy to spot. They always ask about alcohols. They always ask about carboxylic acids, which we'll do in the next video. I think once they've asked the cyanide, okay, this carbonyl, they asked about that a lot. That's very easy to spot. And of course, that carbonyl group will be present in the carboxylic acid as well. And then they quite often ask this CC bond. So we're going to look at those as examples there. Okay. Right.